Welcome everybody to Making a Monster Part 2. So what we did last time was make a monster that had a T-pose animation. We have not done much more than replace that T-pose animation with a limping walk. And if the monster can see us, after 4 seconds it'll start looking for us. It'll do a limping walk and kind of follow us around using a nav mesh. If it loses sight of us, then it will come on, lose sight of me. Gosh, lose sight of me. It's too good. It's too good. It's the predator. If it loses sight of me, then it starts there. Good. Then it starts sort of. Oh my gosh! It starts randomly walking around until it finds me again. And if it is close to me, then it will start stabbing me. I can also shoot it and cause it to seize its existence. So. There's a couple things we could do to improve this. The first thing is the monster can see us even if we're behind it, right? And so if we want to make it a little more realistic, we could give it like a vision cone, right? And so there is a perception system in Unreal Engine, but this actually doesn't require anything more complicated than a little bit of knowledge of linear algebra. So we are going to detour now into talking about linear algebra. So linear algebra, monster, this is its position. Its position in space is 510. And here's the player. Player is over here at 1010. You have like some, X, Y coordinate system or something. How far east of the monster is the player? Rodel, Watana? How far to the east is the player from the monster? 5 units. We know that by taking the player's location and subtracting the monster's location. When you have a vector just means more than one number. What you do is you subtract out the x components, you subtract out the y components. And then you can square them and square root them, but at that point it doesn't really matter. So yeah, if you want the full Pythagorean theorem, it's the square root of x1 minus x2 squared y1 minus y2 squared, or you can just kind of eyeball it and be like, it's 5 to the right. You know what I mean? So this is Mr. Pythag here. So what you can do is you can subtract the difference of the locations, and that is 10, 10 minus 5, 10. Whenever you do linear subtraction, you just subtract out the x components and the y components separately, and you end up with a vector of 5, 0. That is a vector, that 5, 0 vector is what's called a displacement vector. So this vector here is called a displacement vector, which I'll use the fancy colors for. Displacement vector. Okay. And you get it by just subtracting the target's location from the starting location. And so the player is 5 units east and 0 units north of the monster. Now, if we move the player a little bit, move them north. Okay. Player is moved north a little bit. Player is now at 5, 12. What is the displacement vector pointing from the monster to the player? How far east is the player? Oh, sorry, not 5. I'm giving you the answer. How far east is the player? And how far north is the player from the monster? In other words, how far east and how far north? East, north. How far east and how far north is the player from the monster? It is 5 units to the east, and it is 2 units to the north. Again, we can figure that out by doing a subtraction. A vector subtraction looks like this. 5 east, 2 north. Yep. And so how far away is it? We use the Pythagorean theorem. It's 25 plus 4 is 29. Square root of 29 is a number slightly larger than 5. 29 square rooted is 5.38. Okay, so we are 5.38 units away from the monster. And so a displacement vector is telling the monster, essentially, hey, you've got to travel 5 units east and 2 units north, a total of 5.38 units to get to the player. You guys understand? We can do this in Unreal Engine by getting a world position and a world position and subtracting them. That creates what we call a displacement vector. They are very, very, very useful. We use them all the time. So we've got our displacement vector, and there's a couple things we can do with this displacement vector. First thing is we can take the length, which is this, right? Option number 1, give me the length, which is the Pythagorean theorem. Like that. The other thing we can do is we can normalize it. So to normalize a vector, if you have a vector like this with a length of 5.38, to normalize a vector turns it into a unit vector pointing in the same direction, which if I could draw would be pointing in the same direction. Let's see if I can do this a little bit better. It's a unit. That way, close enough. Okay. So you can normalize a vector by taking a vector and dividing by its length. So if you have this vector up here, this displacement vector of distance 5.38, if you just divide by 5.38, well, how does that work? We've got up here 5 and 2, so the vector is 5 east, 2 north. If we divide this by 5.38, the distance, you just divide each of the components by 5.38. And so 5 divided by 5.38 is 0.92, 0.93. And 2 divided by 5.38 is 0.37. And that's our normalized vector. So a normalized vector is pointing in the same direction as before. So if you had a big old vector like that, a normalized vector is pointing in the same direction, it just has a unit length. It has a length of 1. And these are actually really useful. A lot of times you will see game engines and things like that use normalized vectors. A normalized vector has a unit length. This is completely different from a surface normal. There's many different meanings of the word normal. People being normal is also different from this. The normal of a surface is the direction pointing perpendicular to the surface. So the pin here is the normal of the palm of my hand. No matter which way I rotate my palm, that's the normal vector. It's unrelated to this. When you normalize a vector, you are setting the vector to length 1. And normal vectors are usually normalized, so it's a normalized normal vector from a normal person. There you go. Enjoy that. Let that sink in for a little bit. So what can we do with this normal vector here? So we have a normal vector that's like pointing in the direction of the player. That means it's a unit length. In other words, that's the direction the player is from us. So we know how far away the player is. The player is 5.38 units away, and we know the direction the player is. Okay? So every vector has direction and magnitude, right? From Despicable Me, there's a villain named Victor or Vector or something like that, and he commits evil with direction and magnitude. The magnitude of the vector is 5.38. The direction is that way. Okay? What can we do with that? Well, imagine we've got a monster. Let me draw a big scary monster here. Okay. Big scary monster. Okay. And it's looking this way. And the player is over here. Here's the player. The normalized direction to the player is this. The direction the monster is looking is also a normalized vector. And he's looking in that direction. It has a length of 1, length of 1. So the monster is looking this way. Can the player be seen by the monster? The monster is like, right? He's looking over this way. And this guy's like, oh, I'm in a box. Let me fix his spine a little bit. That's a little sus. Okay. Can the player be seen by the monster? What do you guys think? The monster, we're like top down, right? The monster's looking this way. The player's kind of behind him, off to the side. Maybe not entirely behind, kind of like off to the side. No? I mean, maybe. I don't know. There's no real answer to it. What is the field of view for the monster? What do you guys think? How big an angle should the monster be able to see? Right now it can see behind it. Like if you walk up behind the monster right now, it'll do a trace line And it'll see you and it'll turn around and chase you. Okay? What field of vision should the monster have? 30 degrees, 80 degrees, 90 degrees, 180 degrees? If it was 180 degrees, the monster would be able to see, you know, like everything over here, right? 181 degrees, 70 degrees. So, how do we tell if the player is in front of the monster? If the player was here, then the displacement vector would be pointing this way, right? And that's mostly in the same direction as the direction it's looking. If the player is over here, like off to the side, then the displacement vector, normalized displacement vector, is like at a 90-degree angle to the direction the monster is looking. And if the person's over here, then they are behind the monster. So the displacement vector would be pointing that way, and the monster is looking that way. So fortunately, I won't torture you with this, so you probably don't know the answer to it. There is something called the dot product. And this is an incredibly crucial concept in game dev overall. Not just in making monsters, not just in like visibility testing and things like that. The dot product and its cousin, the cross product, come up just everywhere. It's one of the tools, mathematical tools, you have to know. Okay? You have to know it. So let me tell you how it works first, then I'll give you the actual algebra. So if you have two vectors that are pointing in the same direction, the dot product is going to be 1. If you have two vectors at 90 degrees to each other, it's kind of 90 degrees, you'll get 0, or close to 0. It's not quite 90 degrees. Better. And then if you have one vector one way, and you dot product it with a vector facing the other way, you get -1. Okay? And so the dot product actually just gives you the cosine, if you've taken trig, it gives you the cosine of the angle between the two things. So if you have two people that are pretty close to each other, you'll get a dot product of like 0.8 or 0.9 or something like that. And so what you can do with this knowledge is you can have the monster dot product the displacement vector, the normalized displacement vector, with its forward vector. Every object in the game has a forward vector telling you which way is forward. And so in a case like this, the dot product would be like 0.8. In a case like this, it would be around 0.1 or something like that, or 0. In this case, it'll be like -1-ish. Over here, it's going to be like -0.3, something like that for this guy over here, because he's kind of like back and left a little bit. And so what you can do is you can write code that says, all right, well, if the dot product is greater than 0.6, it can see the player. And then you play testing. You're like, let's mess with that a little bit more if it's greater than 0.7, you know. So how do you figure out the algebra for dot product? So let's say this is our normalized displacement vector over here, 0.93, 0.37. And the monster is looking, I don't know, in this direction over here, which is going to be like 0.8 to the right, and like 0.4 down, something like that. 64 plus 16 doesn't quite add up to 1. 0.6. So 0.8 to the right, 0.8 right, 0.6 down. Okay. 64 plus 36 is 100. Okay. So the monster is looking kind of like southeast. Do you guys understand? Like the monster is looking like southeast, and then the player is like, so the monster is looking, so it's kind of like this. The monster is looking in that direction, and the player is kind of like in this direction. The player is at 0.93, 0.37, so it's like east and a little bit up. And this is the look vector of the monster, 0.8 to the right, 0.6 down. So how do we compute the dot product? This one, y1, x2, y2. It's x1, x2 plus y1, y2. This is the dot product. Okay. So, doing this in math, 0.93 times 0.8, 0.744. Is 0.966. So they are very close to pointing in the same direction. So this means the player is in fact in front of the monster. Okay. The dot product we're getting here is 0.96 if I type it in right, which I'm not entirely confident I did. But 0.96 is very close to 1. And so that means the player is almost a little bit off to the side, but he's mostly in front of the monster. Okay. And so what we can do is do all this inside of Unreal Engine. So you can see what it looks like, not just hypothetically. So first thing I'm going to do is turn off the monster's movement because I don't want it chasing me while I'm trying to figure this stuff out. Come over here and rock monster think. I'm just going to turn off the line trace. I'm just going to leave all that code there. What I'm going to do is I'm going to run this down here instead. And I'm going to do probably like a print or something like that. And what I'm going to do is I'm going to compute what were the things that I needed, right? I needed the displacement vector to the player, and I needed the look vector of the monster, and I need to dot product them together. So if I'm going to work backwards, which I could do a dot product like that, and put the output of that into the print string, which will automatically cast it for me. So it will print the dot product of these two. Right now it's going to be printing 1. Well, maybe it's 0. It's not normalized. I don't know. Okay. So we need to get the forward vector of the monster, which is this vector here. And so we can do that by doing, we drag out the, we'll drag out the arrow, maybe. Let's see, because the mesh itself is pointed in the wrong direction. The arrow component might work, but it's also invisible. Maybe we'll just drag out our get forward vector. Okay. And so get forward vector, no. We'll do it from the arrow component then. Yeah, okay. Get forward, let's see if this works. We have the forward vector of the monster. And then we need to get the displacement vector, which is the player's location minus the monster's location normalized. So we've got the player pawn over here. We got their actual location. Okay, great. We've got our world location. Look at that. It's already almost done for us. So to do a displacement vector, you take the actor's location and you subtract the monster's location. So this is what we call a displacement vector here. So we've got a displacement vector, and then we will normalize it. So drag the result of that into a normalize node, and that will take whatever size vector you have there and make it of unit length, make it of length 1. And then that is going to feed into there. Now let's see if it works. So basically, yeah, okay, doesn't want that. Monster VP, and let's get forward vector. Get actor forward vector. Let's try that one. There. Yep. So we're going to get our forward vector and dot product it with the normalized. This is our forward vector here. That's our forward vector. This is the normalized displacement vector, and we're just going to print the results. So we're not going to do anything with it yet. We're just going to print the results, and I can maybe cut down on the delay, starting delay here to 1 or something. Quite so long. If we do this, we should start seeing numbers appear on the top left, and 0.95, 0.98, or 1 means I'm directly in front of it. 0.98, 0.96, over here, 0.5, over here, almost 0, 0.3, 0.4. So you guys think that it should be able to see me from here? What do you guys think? It's 0.5, and this is one of the things that I do. I'll just put it into the game. I've disabled it running around so it doesn't screw anything up. But basically, I just look at these numbers. I'm like, 0.5 sounds about right. I don't know. So 0.5, you think it should see me? All right. What about here? 0.25. Kind of off to the side a little bit. Yeah? What about here? Negative 0.2. When it's negative, I'm behind the monster now, right? Should still see it. What about here? Directly behind it's around negative 1, right? So negative 0.5. No, not there. What about here? 9. Negative 0.7. I think. Should it hear me, maybe? No. But here, you guys think so? I mean, I can see its eyes, so, maybe it can see me. What do you think? This is at negative 3. I'm already behind it. But it's kind of like as it's running and limping along, it maybe you can see me. What do you think? And this is literally how I do game dev. Like, I'll just sit there and I'll just print values out. And just walk around and be like, does this feel like he should be able to see me? I don't know. Should it, that's the gray area? Okay, so maybe come forward a little bit. This negative 0.5. Yeah, it's just something you have to choose for yourself. So negative 0.5 is what we're going with here. Okay, so if the monster, we're going to take this and we're going to compare it. If it is greater than or equal to, use negative 0.15 as the cutoff. So that's like 190 degrees of vision, something like that. So in calculator terms, negative 0.15, trig inverse cosine. So it's 98 degrees in both directions. So it's 196 degrees field of view. So it's 196 degree field of view for the monster right now. So if this is true, then do the rest of the code. Right? Only, actually, I don't know. Maybe not here. Maybe not here. Maybe we'll do this. Okay. So if I'm in front of the player, then it will do the line trace to see if it can see me. If it can't see me, then we're just going to randomly move. Okay. You guys see what I did there? So this code here is saying, is the player in my field of vision? In other words, is it within a certain angle of my forward vector, the direction I'm looking? If it is, then we will check, we'll do a line trace. We'll shoot a ray between me and the player, and if it hits a wall, can't see him. If we hit the player, then we chase him, right? So we both need the player to be in our field of view and have no walls between us. And there's one other check we're going to have to do. But for now, if both those tests pass, if they're within our field of view and within the ray, then the ray didn't hit anything, then we will chase after the player. If we could not see the player because there's either a wall in the way, like that, or because they're behind us, then we will just randomly move around. We'll just randomly walk around the battlefield. There's one other thing we should do, and that is the maximum sight distance that it can see. It's really annoying in video games when monsters can see you across the map and just shoot you, or something like that. So the other thing we should check for is the how far the player is, right? So we can do that. Here's our displacement vector. We can do that by getting the length of the vector. So this is so by getting the length of the displacement vector, then we can tell how far away the player is. So how far should we allow the monster to be able to see the player? What do you guys think? So this number here is how far the player is away. So in my opinion, if the player's on like the far side of the world and, you know, sure, they've got line of sight, sure, they're in front of us, they still shouldn't aggro. Like there should be a maximum sight radius, you know, on the monster. So how far do you guys think the monster should be able to see? What do you think? 100 meters. Okay, so we'll drag that out. And we will say if it is less than or equal to 100 meters. So 100. Okay, what happened here? 100. Weird. Okay, 100, 0 per centimeters, right? So if the player branch again, and we'll just link this up like this. So we first check to see if the player is within 100 meters. If he is, then we check to see the player's in front of us. If he is, then we do a line trace and see if he's visible. If he is, we move to the player. If any of those things fail, then we just randomly mill about doing nothing in particular. So now we should... did I put it back on? I guess so. All right. So here comes. He's chasing me. He's chasing me. I'm gonna try and get some. Distance between 100 meters is actually really far. Right, it's still doing the line trace, so I'm not 100 meters away yet. Maybe no, still. Yeah, maybe I should make that shorter. Make it 10 meters. There we go. And we can put it back up to 100 for the finished product. But I want to test to make sure that it's only going to spot me within 10 meters. Yeah. So I come out here, you can see that I'm not having any lasers shooting at me. It's not even doing the trace line if I'm too far. If I'm too far away, then it does not do the trace line. Okay. But if I get close, where'd he go? Ah. Where'd he go? Just wandered off. Bro. And just launch it again. You can see me. It's chasing me, damaging me. Now I'm over here. He's still trace lining me. I can get 10 meters of distance though. He will break off pursuit. You see that? So once I got far enough away, he just sort of gets bored and randomly walks off. Now if I get close to him again, now see he's looking away from me, so it didn't do the trace line. But if I'm, yeah, there we go. I'm in front of him, it did the trace line. If I'm in front of him and within 10 meters, it'll do the trace line, but the wall blocks it, so he's not chasing after me. Okay, this one should trace. There you go. But the wall blocked it, so it didn't do it. So even when I'm behind him over here, even if I'm within 10 meters, he is not looking for me, right? Because he's not spotting me. If I come over here, I might be stuck on something. There we go. All right. So he's got good peripheral vision, so he should be able to. There we go. There you go. All right. Chase after me. There you go. So as long as I stay within 10 meters, he will keep coming after me. All right. I died. You guys understand? I can put the distance up a little bit more, maybe 20 meters. So the displacement vector is one of your most crucial, most important tools in all of game dev. It's used all over the place. If you go up to a vending machine and use the vending machine in a video game, you take the displacement vector from the vending machine to the player, normalize it. That's the direction the player is from you. Then you cross product it or dot product it with the direction the vending machine's looking. If they're pointed in opposite directions, that means that the player and the vending machine are looking at each other and you can use it. If you're pointed the same way, that means the user is behind the vending machine. Let me draw that out for you. So if you've got a vending machine, selling snacks, right? And the vending machine's looking this way. If the player walks up behind the vending machine and he's looking the same direction, the displacement vector, the dot product is going to be of the, if this is the forward vector of the player, and this is the forward vector of the vending machine, if the dot product is 1 or close to 1, that means they're both looking the same way. And that means that the player is behind the vending machine. And you shouldn't allow him to use it, right? Because it makes no sense to be able to use a machine from behind. But if the player was over here and the forward vector was looking this way, if you got a dot product of -1 or around that, the vending machine's looking one way, the player's looking the other way, that's a -1 dot product, right? Then that means the player's looking at the front of the vending machine, and you can allow it. Okay? If you want to do a backstab, so here's a person with a knife, and in a lot of video games, if you hit somebody from behind with a knife, here's the innocent target. This is the direction the person's looking. This is the direction the person's looking behind him. What dot product should we allow for assassinations, for backstabs, for double damage from behind? So this is the forward vector of the guard or whatever. This is the forward vector of the player. The dot product equals what for a backstab? What values should we allow for a backstab? They're both looking the same way, right? So what kind of dot product is that going to give you? If the two vectors are pointed the same way, what number do you get? Rodell, Watana? If you've got two people looking the same way, what number are you going to get from the dot product, roughly? You'll get a positive number. Remember, if they're looking in opposite directions, you'll get -1. If they're looking the same way, you're going to get +1. If they're looking mostly the same way, you're going to get like 0.8. Okay. So what values should we allow for a backstab? Just 1, you're almost never going to get 1, right? Exactly. That means that you have to be like pixel perfect behind the person, right? Like we want to allow somebody, like if they're just like kind of behind, like this person's looking this way and this person's looking this way, we still want to allow that to be a backstab because they're mostly behind the person. They don't have to be perfectly behind the person, right? 3 to 4, there is no 3 to 4 in dot product world. All the numbers range from -1 to +1. What the dot product is, it's the cosine of theta. It's the cosine of the angle between their two forward vectors. So if one person's looking this way, one person's looking that way, it's the cosine of the angle between them. Cosine always gives you a number from -1 to +1. So what values should we allow for backstabbing? What do you guys think? .8. Like you saw the numbers when we were like walking around. 0.15 is kind of off to the side. 0.8 is like right in front. What do you think? How narrow a range are you going to allow people to do double damage with the knife in? anywhere behind. Anywhere behind would be greater than or equal to 0. Greater than or equal to 0 would be any point behind the person. Any values below 1 higher than 0? Yeah, well, yeah, 0.5 maybe. So 0.5 would be a 60 degree. So it's 120 degrees behind the person. So you'd have like a 120 degree arc that you'd be able to stab the person from behind in. That seems reasonable. My point is that the dot product is used everywhere. So yeah, it's easy to say, oh yeah, I understand this, sure. But like you need to actually go out and do it. And so that's what your homework is going to be for today. So I want you to add these restrictions on the monster. And then I want the player to do double damage if they are behind the monster. Okay. And so the tools that you need to succeed, you can get the forward vector. That is the direction you're looking. You can get the forward vector of the monster. You can get the forward vector of the player. Okay. And I want you to figure this out instead of just copying my blueprints. Normal. I want you to figure it out. Show me you understand dot product. That when the player shoots the monster, it instant kills them if you shoot them from behind. So you shoot them here, they die, sure, whatever. But make it so that if you shoot them from behind, you one-shot them. Okay, so coming over here. If they're looking away from me, come back. If they're looking away from me, that would have instantly killed them. Okay. So shot from behind, but instant kill. Show me that you understand dot product and displacement vectors and forward vectors and all that other stuff. Okay. Okay, so what else can we do with the monster? We can have better animations. We've got range. We've got field of view. I feel like it's a pretty good place to stop. We'll just stop here. We can talk about cross product another time and the uses for that. So displacement vector is the direction from one target to another. And once you have a displacement vector, you can get the direction and you get the magnitude. And these two things are useful in a lot of situations. How far away is the player? If the player is within 20 meters, continue. If they're not within 20 meters, don't continue. You dot product the direction that they are with our forward vector. If we get a number above, in this case, what do we say, -0.15, so like in a 190 degree arc, if they're within that arc, we can see them theoretically. Can continue. Do a line trace. We throw a ray through the world from us to them. If we hit them, that means they're visible, and then we charge them. If any of those things fail, then we just mill about randomly. And that is our class for today. Thank you for coming out, everyone, and I will see you on Tuesday. Peace.